Okay, hello everyone. I'm very happy to have Swagato here with us today. Swagato has spent more time in STCS than me, so it is great for me to introduce him. He was a student here from 2011 to 2017, and that makes it 6 times longer than they want to have spent here. Hopefully, none of the students have seen him though. Hopefully, all of the students after they have graduated. So after that, he went for a postdoc in US, and now he's a faculty member at Kharagpur, and he'll be talking about query complexity of composition of functions.
Thanks, Raghu. Yeah, it's great to be back here after quite some time. So Boolean functions are central objects of this talk, familiar objects, but let's refresh our memories. A Boolean function maps each bit string of a certain length to a single bit and is represented by its truth table, which simply lists its values for every input bit. Okay. So
Go on.
yeah, go ahead.
No, the video is on it.
All right. So this is
Click on the slides. Just click somewhere on the side.
okay. So this is the outline of this talk. So let's talk about a model of computation called the query model. So that I'll introduce to you in the first part. And in this talk, we'll analyze complexity of Boolean functions with respect to this query model, and we'll focus on a class of Boolean functions called composed functions that I'll introduce in the second part of the talk. And in the third part, I'll introduce the composition question, which is an umbrella term that encompasses pretty much any question that one could ask about composed functions in complexity theory. And we'll instantiate it for the model of computation that we are studying in this query model. And in the final part, I will talk about our findings. So with this, let me introduce the query model to you. Sorry?
Sorry, messed up this.
What happened? Something.
Slide.
So let me introduce query model through an example. So let F be this 3-input Boolean function and a query algorithm or a decision tree for F is an algorithm that given an input bit string x1, x2, x3 in this case computes a of x1, x2, x3. Let's denote the string by x, and the algorithm is given query access to the bit string. So the algorithm can query various locations of the string, and we'll assume that there is an oracle who answers those queries. So let's see an example. So this is an algorithm that queries the first bit of x, and there could be two possible answers, 0 or 1. If the answer is 0, then the function simplifies to x2, and which is what the algorithm asks, and the value of x2 determines the value of f. And if, on the other hand, the value of x1 is 1, then the function simplifies to x3, and the algorithm asks for x3, and the value of x3 determines the value of f. So the variable that is queried at each step will potentially depend on the answers to the previous queries. So it's an adaptive computation. And the execution of such an algorithm can be modeled naturally by a rooted full binary tree, where you have internal nodes. Each internal node has 2 children, and each internal node is labeled by a variable which is said to be queried when the computation reaches that node. And the computation and each leaf, so the computation terminates at a leaf, and each leaf is labeled by a bit which is said to be output when the computation reaches that leaf. and such a tree is said to compute a function f if the output of this process for every input bit string agrees with fx. So if you run this process on an input bit string x, it agrees with fx for every bit string x. So this decision tree computes the function f written up there. And the complexity of such a tree is the depth of this tree, which is the number of queries that are made in the worst case. So this is a function that depends non-trivially on 3 bits. However, this algorithm makes 2 queries in the worst case. So it's possible to decide a function by querying fewer bits than the function depends on. Yeah, and no other computation matters, only the queries. So we won't ask how does the algorithm find out what to query next, how much computation does it take for the algorithm to find out as well. Only the queries. And yeah.
And so the depth can depend on the order in which you are doing the query, the order of the variables. Like, so here you are saying first x1 and then.
Yeah. So a different tree which computes f will have a different. Can be structurally different. So DFF is the deterministic decision tree complexity, or the deterministic query complexity of f, is the depth of a shallowest decision tree that computes f, or equivalently the number of queries made by the best decision tree, or the best algorithm in the worst case. So this talk is on randomized decision trees. So a randomized decision tree can be defined in various ways. There are various equivalent definitions. The view we'll adopt is that it's a probability distribution over deterministic trees. Yeah. So let's see an example. So here you have the 3 input AND function, and consider this tree. Consider uniform distribution over 3 deterministic trees, each of which queries 2 of the 3 variables and outputs their bitwise AND. Yeah. And running this tree on an input means sampling one of these trees uniformly at random and running that deterministic tree on an input. So the number of queries, the query complexity of such a tree is the largest depth of any deterministic tree in the support of this distribution. In this case, it's 2. The number of queries made in the worst case.
No, but 2 does not supply usually. If you query only x1, x2.
No, so then so you'll tolerate some error, and you can verify that on every input bit string, this tree produces an erroneous output with probability at most 1/3. If the bit string is, for instance, all ones, you are correct with probability 1. If there are at least 2 zeros, then you are correct with probability at least probability 1. So if there is, let's say, 1 0 and 2 ones, then the value of AND is 0. But this tree may output 1 with probability 1/3, and that is the worst case situation. So this success probability, the error probability of 1/3 is worst case over all inputs. So it's a probabilistic guarantee, but a worst case guarantee, worst case over inputs, and the probability is over the randomness of this probability distribution. So R epsilon of f is the minimum complexity of a randomized decision tree that computes f with error probability epsilon. And R of f is defined to be R of 1/3 of f. This choice of 1/3 may appear to be arbitrary, but if you're familiar with randomized computation in general, you would know that this 1/3 could be replaced by any constant, strictly less than half, without affecting the measure by more than a constant factor.
So this is the height of the largest tree in the support.
Sorry?
So R of epsilon of it, this is the height of the largest tree in the support.
Height of the largest tree. Yeah. So the depth of a given randomized algorithm is defined to be the depth of the largest decision tree in the support. Alright, so decision trees are can be motivated very well theoretically as well as practically. I'll be glad to talk to you offline about it, but for now, let me skip this slide. So yeah, but please ask me later afterwards. So let me, as I said, we'll analyze the complexity of a class of functions under this query model, and they are called composed functions. So let me tell you what they are. So let's say f and b are 2 functions on n bits. They don't both have to be on n bits, but let's assume that for simplicity, and nothing much is lost. Because of this assumption. Then f compose g is a function on n square bits that is defined pictorially by this depth to tree. So think of this tree as a Boolean circuit with F and G gates. Yeah, so you partition the input bit string into n parts of n bits each. You apply G on each part, and this gives you n bits. Apply F on those n bits, and the output of that application of F is defined with the output of F compose G on this bit string. So there is a rotational abuse here. F compose G power n is probably a more appropriate, as Raghuvansh was pointing out earlier, but I'll use F compose. So this is F compose G, and F compose G is a well-studied object in complexity theory and as well as elsewhere. So in general, it models situations where outputs of a bunch of identical tasks feed as input into another task. So such situations are found quite abundantly in practice also or elsewhere. But in complexity theory, compose functions are one of its uses is to construct explicit functions that are hard with respect to various models of computation. All right. So composition question, as I said, is an umbrella term that encompasses pretty much any question that you can ask about compose function. So so this is composition question instantiated for decision trees, but let me talk a bit generally about composition questions. So the definition of compose function immediately suggests an algorithm to compute it for various models of computation. And composition question asks whether that algorithm is an optimal algorithm or there is another algorithm that's structurally very different and much more efficient. So let's see for decision trees. So it's fairly easy to see. We'll go through the argument that D of F compose is at most df times dg. So why is that true? So let's say the blue tree on the left is an optimal decision tree for F, and the violet tree on the right is an optimal decision tree for G.
Can I ask a stupid question? So when you look at the query model, it's obviously at most the number of variables.
Yes.
So when you measure it, is it a fraction of n or is it just the number?
Just the number. Think of it as a function. It's a matter of scaling, dividing by n.
Yes, but composition also increases the number of variables, so it will not affect the fraction that much. The number.
This is just the number. So you ask this question for the standard definition of very complex, which is the number of variables.
Okay.
Yeah, so I can establish this inequality only when D stands for the number of variables.
If it's a fraction, then the denominator is.
Yeah, the denominator is the
same, right? Then square on the left, square on the left, and each of
Oh, it doesn't, it's the same. Yeah.
Oh, yeah, actually.
Yeah. Yeah. Totally. So, okay, so coming back, let's say the blue tree is an optimal tree for us and the violet tree is an optimal tree for G. Then you can put them together to construct a tree that computes F compose G as follows. So this diagram is a bit misleading. So what you do is that you simulate the blue tree, and whenever it issues a query, you realize that in the definition of F compose G, inputs to F are outputs of copies of G. So you solve the corresponding copy of G by invoking the violet tree and feed its answer back into the blue tree. So you spend DG queries to serve each query of the violet tree, blue tree, and the blue tree makes DF queries in the worst case. So in total, you make DF times DG queries at the most. Is that all right? There's a question. So D of F compose G is at most DF times DG. So how about randomized? So a similar sort of argument works out, except that the violet tree is now a randomized tree and will produce an erroneous output once every 3 times on an average. But there are standard ways to deal with that by reduce the error and make it small enough so that it becomes manageable, and tolerate blowout, which is hidden in this order tree notation. So let's say R of F compose is also at most R of F times R of G. So composition questions for us are whether this bounds are optimal. For the deterministic case, this bound is known to be optimal, and is long known from the works of Tal and Montagu.
Sorry, what is the meaning of optimal? That for every FG or there exists FG?
They're just actually. Right.
So I think for the deterministic case, it's true that for every FG, but for optimal, it means that there exists.
No, but every FG, F or G could be something like where you
Yeah.
very easy on the output space of G.
What if J is a constant?
Give the code, it will be 0 on both sides, so it's true.
No, but
No, let's say G is X bar.
yeah. Okay.
Or so in general, let's say optimal means there exist F and G for which. Okay, so the randomized composition question is still open, and it's a topic of this talk. So let me tell you a bit about the past works on the randomized composition question, query composition question. The past results fall into two categories. So the first one out of the form R of F compose G is at least asymptotically R of F times M of G, wherein M is some measure of complexity, which is at most R. And the second category of results consists of results of the form R of F compose G is at least M of R, M of F times R of G, wherein it is some measure of complexity.
So M of G is at most R. What is this R?
R is the randomized variable. The R that's written. M of G is at most R of G. Oh, R, sorry. And for both categories of results, people have nailed down the asymptotically largest measures M for which they can be provided.
Wait, what does this mean? Nail down.
So they have shown that R of F compose G is at most R times LR of G. Look at the left result. Yeah.
Okay.
They have furthermore shown that for any M for which R of F compose G is at least R of RF of MG is true, LR is omega of M.
Okay.
Let's repeat again.
So they have shown that for any measure M for which this is true, yeah, LR is asymptotically at least M. So LR is the largest measure M for which this statement is true.
So all you have to show is that LR is almost the same as R.
Yes. So Kavita is.
So I didn't get it. What is LR?
So LR is a measure that these authors introduced, and I won't define it. So LR is some measure that these authors introduced, and they showed that R of F compose G is at least R of F times LR of G, and they further showed that if for some other measure one shows that R of F compose G is at least R of F times M of G, then LR is at least M asymptotically. So LR is the largest measure M for which R of F compose G is at least R of F times M of G is true.
Is it?
And how, like, what do you know about LR of G versus R of G?
So LR is at most R.
LR is at most R. That I agree.
If it is the other way around, then it will resolve.
Sorry,
Is there a separation you can do?
I'll talk about that.
That's what you talk about. Okay.
Yeah,
Is there an upper bound in terms of LR?
upper bound of what?
Of R of G in terms of LR?
Yeah, there is.
Sorry, not R of G. Is there an upper bound of R of F compose G in terms of R of F and L of G?
So LR can be upper bounded in terms of R itself. So that will give you a number. So LR is at most.
So you know that people replace, I mean,
So LR is at most R. I'm not sure.
No, I'm saying I have to upper bound R of F compose G in terms of R of F and LR of G.
Upper bound R of F compose G in terms of R of F times LR of G.
Yes.
So
then it replaces omega by O.
yeah, so LR of so R of F compose G is at most R of F times R of G, right?
Yes.
And R of G they showed is at most LR of G square. Yeah. So so there is an upper bound of R in terms of LR.
But it's quadratic.
It's quadratic. So they are polynomially related.
Okay.
Yeah. So one can
That's right.
so if there's no further question, I'll continue.
But it's not known, like you cannot, for all we know, this may be you may have R of f times LR to the 1.5.
Yeah, for all we know.
Okay.
So I'll talk about this soon. So this talk deals with the left kind of results. R of f composed is at least R of f times energy. So let me tell you a few more results of this kind. So the first one is the one shown in the previous slide. R of f composed is at least R of f times R of g. The second one is R of f composite is at least R of f times chi bar of g, which is for another measure chi bar that this Gavinsky et al. Introduced in 2019. I was part of this work. It's called max concrete complexity, and I'll state these three results. So R of f composite g. The third one is R of f composite is at least R of f times Rs of g. But Rs of g is a measure called the sabotage complexity measure, defined by Ben, David, and Kothari in 2015. So now LR is at least, so these inequalities are asymptotic. So LR is omega of chi bar is omega of Rs. So the first result subsumes the second one subsumes the third. Yeah. Okay. So however, no asymptotic separation is known between any two of these measures. Yeah. So for all we know, they all could be the same asymptotically. For partial function, I'll talk about total functions only. So for more general objects called partial functions, which are a generalization of Boolean functions, they have demonstrated asymptotic separation. But for Boolean functions, there is no. So this is what I said earlier. R is the largest measure for which this is true. So determining whether a perfect composition theorem is true is equivalent to determining whether LR and R are asymptotically the same. Yeah. So
what does LR stand for?
they call it a linearized complexity measure. I haven't defined it in this talk, and I will do some measure.
Linearized random.
I do not know whether they call it linearized complexity measure and they use the notation LR. So
You're right.
It's probably linearized random decision tree.
something like that. Alright, yeah. So the question of finding out whether or not a perfect composition theorem is true for randomized query complexity is equivalent to determining whether LR and R are the same asymptotically. And so we asked whether chi bar and Rs, how do they compare with R? As we said earlier, there is no asymptotic separation, and all of them being equivalent to one another asymptotically and equivalent to R is a possibility. And maybe analyzing one of the others will be easier. Yeah. And so this motivates this work. So in this talk, we'll compare Rs with R and talk about, we'll compare Rs with R, and I won't, there won't be any further mention on chi bar or LR. So the rest of the talk is focused on comparing Rs.
That is actually.
That I'll tell you, but I won't.
This is the sample.
Yeah, what's this? Yes. Oh, you wanted to know what RS stands for? I'll define RS for you.
Next, it's not my name.
Okay. So let me define Samaras complexity measure. So let's say G is a Boolean function. So RS of G is the minimum query complexity of a randomized algorithm R, randomized decision tree R, with the following guarantee. So I'll write down a statement next. So for every pair XY of input bit string such that Gx is 0 and Gy is 1, that is R when run on X, it's not written here, so doesn't matter. So R when run on X queries an index on which X and Y differ with high probability. So R distinguishes the two pairs X and Y. So whenever you run R on X, it distinguishes it from Y.
There exists some index to J.
There exists some index. So R queries some index set. That's what it is. Some index set on which X and Y are given. With probability at least 2/3. So the probability guarantee holds for every pair X and Y, and the probability is over the randomness of R. Is the definition okay?
Is it asymmetric? So you're just saying Rx queries or also RY?
What is the input to R, X or Y?
So R is a decision tree that queries various locations of the input bits.
Okay.
And it satisfies this guarantee for every X and Y. Okay, so a decision tree when run on X queries an index where they differ. If and only if the decision tree when run on Y queries an index where they differ. Same thing. So yeah, more questions on this definition. So one thing I'd like to point out here is that the output of R is irrelevant. So we may think of R, the decision trees in the support of R, the deterministic trees in the support of R, as decision trees with unlabeled leaves, because their output is with unlabeled leaves.
Unlabeled.
Yeah, their outputs don't matter, right? So this guarantee has nothing to do with their outputs. Yeah.
So it doesn't say that
Huh?
we sort of capture the correctness with probability 2/3 in some way.
No, like it's not clear. Then you would prove that RS is equal to R. Yeah. So yeah, so let's say you have two bits in two bit strings X and Y. X is X1 through X and Y is Y1 through Yn, and Gx is 0, G1 is 1. And let's say you have a string that that queries the second bit of its input. And let's say for this pair, both the query outcomes are both 0. So then yeah, you go to its left child, which queries the 6th bit. Both are 1, go to its right child. Both are 1, right child, which queries 4. And let's say here the 4th bit of X and Y are different. Then you have distinguished X and Y and have spent 4 queries. Yeah. Yes. Okay. So Benjamin and Kothari asked whether RS and R are the same, which is probably Kavita's question. Yeah, and if RS is equal to R, RS and R asymptotically, then yeah, you also have a perfect composition here for randomized pericomplex. So this also is interesting in its own right. It captures the question of relative difficulty of distinguishing two inputs on which G is different versus classifying a given input. Yeah, so classification. So classification is at most as hard as classifying, but is it strictly easier or?
How does it capture the fact that it distinguishes?
Sorry.
How does it capture the fact that it distinguishes?
Oh, so RS. So this definition. So this guarantee says that RS is the minimum complexity of a randomized algorithm that distinguishes any pair X and Y on which G, the value of G are different.
Yeah, it queries an index where they differ, but why does it?
Yeah, that's
Maybe the output is not dependent on that query.
No, so but until you query an index where they differ, the inputs look alike to you.
Yes.
And then the moment you query an index where they differ, you distinguish the two inputs. You find the position where they differ.
Yeah, but maybe you forget that position.
Sorry?
Maybe you forget that position later.
That's okay, but the transcript of the algorithm are different for the two runs.
If that this algorithm exists, then I can write another algorithm. Because yeah, that's what you're saying. You have the transcript saying.
Yeah, so the transcripts of the two runs, if I look at them, they will be different for X and Y. So let's say this is what we mean when we say that the algorithm distinguishes X and Y. Yeah. On the other hand, R captures the difficulty of classifying a given X into one or two classes. X equal to 0. And this, as I said, question investing in this talk. And Benjamin and Kothari showed that RS is at least square root up to the factors. So distinguishing is not too much easier than classifying. It's quadratically equivalent. And so the question is whether
Any Boolean function. This is for any Boolean.
any Boolean function. Like there are partial Boolean functions for which it's not true, but in this talk, I'm talking only about Boolean functions. So the complete table where all the entries are 0 and 1. Full, what is it called? Total Booleans. Yeah. Continue.
The randomized decision tree give us one such procedure.
Sorry.
Randomized decision tree will give us one such procedure to distinguish.
Right. So yeah. So RS is at most star. That will show RS is at most star.
Yeah.
And they show that RS is at least square root of R. So RS is between square root of R and R.
And how does this affect the composition result?
This is how. So out of F composite is at least out of F times square root of R of G. They have just plugged this bound into their composition result. So they showed that out of F composite is at least out of F times RS of G, and they showed RS is at least square root of R. This is what follows from their work. So let me tell you what we do.
Sorry, so why is it called sabotage? Because
Not pretty sure, but it looks like yeah. So they define it slightly differently, the original authors. So they said that you have a string over a larger alphabet 0, 1, star, and dash or something, and such that there are multiple ways of filling up the non-binary locations to make the string 0 or to make. Probably that's what they mean by sabotage. Filling up the unfilled entries in a way to turn it to a 0 input or a 1 input. I do not know. Yeah, so to build up towards what we do. 30 minutes. So I'll have
This is a bit slow in Boolean.
Okay, so distributional penny complexity. So distributional complexity, many of you would be familiar with for various models of computation. So for d mu of G, so let's say mu is a probability distribution over the domain of G, which is the set of all binary strings of length n. And d mu of G is the depth of the least depth of a decision tree that computes G with probability error probability at most 1/3 on a random input sampled from mu. So here I have a deterministic tree, and the probability is over the randomness of the input and the error probability. So such a tree will err on at most 1/3 fraction of the input, but the fraction is with respect to mu. So the minimax principle establishes a connection between randomized and distributional complexities. So R of G, this is a straightforward application of von Neumann's inverse principle to decision trees, and it states that R of G at most the maximum distributional complexity for any input distribution. And then this is a restatement of the composition question in light of this. So it asks whether R of F composition is at least R of F times maximum of D mu over any mu. So, a probability distribution over 0, 1 to the n, in which each bit is an independent Bernoulli random variable. So each bit is independently distributed, and Bernoulli distribution is the only distribution for a single bit. So such a distribution is called a product distribution. We call it a product distribution. So each bit is sampled with. So the first bit is sampled. The first bit is 1 with probability 3/4 and 0 with probability 1/4. The second bit is 1 with probability 2/3 and 0 with probability 1/3 and so on, independently of the first. And we define D prod to be the maximum of D mu G, but only over the product distributions, only over product distributions. So D prod is at most R, because R is the maximum of D mu over all distributions mu. D prod on the other hand is maximum of D mu over a smaller class of distributions mu. This is very good continuous principle. So this is the first main result. We show that the sabotage complexity is at most D prod. Yeah, at least. Sorry, at least T prod asymptotic. There are no factors. Yeah, so Ben David and Kothari's question was whether RS is at least R. That is whether RS is at least the maximum distributional complexity over all mu. What we managed to show is that RS is at least the maximum distributional complexity for over all product distributions. And as a theorem one together with their composition immediately gives this R of F composition is at least R of F times T product.
Do we know that R is atmospheric quadratic in a D prod?
No, like I don't know. Yeah, so none of these results will beat the base that we know because people have nailed down the largest pressure M for which such results are true. So the whole point of all these is to relate RS with R. Understand RS in this. Now, could it be the perfect composition theorem? So can it be the case that for every G somehow the mu that maximizes d mu G is always the product distribution, So one may think that you see in a product distribution, varying one variable tells you nothing about any other variable. So maybe the hardest distribution is always a product distribution. Not true. So we show that we exhibit a function which witnesses a polynomial separation between D prod and R. So and the function is the well-known function that's extensively studied in this area, the complete binary NAND tree. And we show that D prod, the maximum distributional complexity over product distribution, is polynomially smaller than the maximum distributional complexity over all distributions with R. How much is omega? How much? What is it? Don't remember. Some irrational numbers.
Like square root.
There are square roots. Square root 17. I don't exactly remember one. Something like that.
But it's below one.
Huh? No. So some expression that involves square root 17.
Is it around 0.1? Is it around 0.2? Is it around 0.3? What is it?
I thought you some expression which I never bothered to write. Calculate.
Somebody got to the point that you figure this.
No, some expression that involves square root 17. I think
Maybe it's square root 17 minus square root 17 plus 1 over 4.
no, I think it's irrational.
I'm also irrational.
So in the rest of my talk, I'll tell you the ideas that go into the proof of this, that RS is at least deeper. Any questions so far? So we do this via another measure that we define in this work. So to build up towards that, let me introduce some definitions. So let's say capital T is a deterministic decision tree, and L is a leaf of T, and here you have an amplified view of L. And let's say mu is every string leads the computation of T to some leaf. So let's consider strings that lead the computation of T to L, and identify those strings, the set of those strings with L. By L, I mean the collection of those strings that lead the computation to L. Then let's look at, let's say mu is a probability distribution that's supported on L. And now G is a function, and we will induce a bipartition on L. And you look at the volume of the smaller of these two regions. That is we define error of L with respect to mu to be that volume, the smaller of the two. So it's a measure of how biased the leaf is with respect to mu. So if it's very close to 0, then the leaf is highly biased. If it's close to half, then the leaf is unbiased.